Okay. So there we have for the presentation today, indices and exponents. So the presentation outline covers an introduction. You have definition of indices and exponents. You have rules and properties to look at. Then we'll look at worked examples, a couple of them, and then I'll talk about some application of these indices and the exponents. Okay, then we'll conclude. So that's what we have as an introduction. I'll talk about what these particular indices are. So, as an explanation for indices, the question to be answered is what indices are and how they are used. Okay, and then we note that when you come to indices, they are basically looked at as indicators or pointers. Okay, indicators and pointers. So we normally have a presentation or the notation in the form of, for instance, we have b to the raised power n, where b is taken to be the base and the n is taken to be the exponent. So normally this type of presentation is reserved for numbers that are multiplied by themselves several times. Numbers that are multiplied by themselves several times. So we actually present this particular notation. Okay, so let's look at exponents further. When we're looking at the exponents, okay, we need to know the difference between a base and exponent. As I've already mentioned, a base and exponent. The exponent can also be taken to be a power. Okay, the exponent can also be called the power. So that's what you should know. Okay. Now we need to look at rules and properties of these exponents. Okay, so I have presented here a number of them, which are supposed to be the principles which we are going to apply whenever we are confronted with the mathematical operations of this nature. So that's what we are going to look at. For instance, the first rule is showing you that you have a base A, which is the same as the other one, here A, but the powers are different. Here it's M, here is N. So when you have a common base, but the exponents are different, and then you are multiplying, the rule says that you get the base, as you can see here, number 1, the base is the same, you simply add the powers, or you simply add the exponent, you get the same type of answer. So a to the power m times a to the power n is equal to a to the power m plus n. Okay, so that's what you should remember. So let's
the slide isn't showing.
Okay, let me just get that. Are you able to see the slide now? Hello? Are you able to
yes,
see?
I am.
Okay, fine.
Yes, I can.
Okay, great. So I was talking about the first rule, okay, where you have a base A raised power m, and then you have the base A raised power n. Now in this case, what we are seeing is that the two are multiplied. So when the two are multiplied, the rule says that it's the same as getting A, which is a common base for these two factors, and then simply add the powers, m plus n. You get the same answer. Okay? You get the same answer. So let me illustrate this one in this manner. Okay. Let's say, okay, look at this. Okay, let's say I have this. Okay, it's the same here. Well, let me just use this one. Show this one. Okay, there we are. So that we have a similar one. So let's say that in this case, just make it bigger. Okay. Let's say in this case the base is 4 and the power is say 2. Again here the base is the same one. The base is the same one, which is the 4. Yes. The same one, 4, but the power here, the power is 3. Okay. Or let me make it simplified. The power is 1. No, when 1 is the power is not. Let's say the power is 2 again. Yes. Okay, fine. So what it means here is the common. There is a common base of 4, which you put here. Okay. Then here you just add the 2 powers. There is the first one is 2. Just is 2, then plus 2. Okay, so that's what you have, which is going to give you, let me just get this one, you get this one. Okay. Okay, so you have in this particular case, when you add the 2, you have 4 there. Have you seen that? So that's what it means. So you're applying the first rule. You apply the first rule. Okay? So that's what happens. So we are looking at this first rule, which we played around with this one. Okay? So that's what we have considered in this particular case. So when that is the case, so you work out this one, what does it give us? What does it give us? Is equal to 4 times 4, like saying this one. We have just give you this one.
Yeah, so masters and the,
okay.
The degree masters.
Okay. So it's 4 times 4 times 4
it's now
times
making
4.
Way of making money. Yeah, because
4 times. So the answer will be 256. Okay. So that's how you resolve that
So what I'll
one
do now is
using the first rule.
like guys, I can
Okay.
load these papers.
Then we look at
Because they are saying it
the
takes
other
about 14
example. The other
Yeah, now they have
example
to go and
is this one,
switch up from
rule
this
number 2. How do you deal with rule number 2?
Yeah, so let me
Again,
mark my-
you look
Let
at
me
this
finish my
particular arrangement. Okay, look at this particular arrangement under rule number 2. Rule number 2. If this one was rule number 1, what is rule number 2? Okay, rule number 2, that's what we want to work with now. Okay, so rule number 2, we are looking at this rule. So let me make it bigger. Okay, so now there we are. Let me come up with a simple illustration. Simple illustration. Let's say here we have 4 again, and here we have 2, and here we have again 2. Okay, so what it means is that when you have this type of arrangement, the common base raised to a power, then everything raised to power n, the common base raised to power m, then everything raised to power n, the same as common base raised to power m times n. So this is what I'm demonstrating here. So in this case, this is what you are going to see. You have 4 there, which is the base. Then you have 2, which is multiplied by again 2. Okay, so that's what we have there. So meaning that we're going to have this equal to, let me write it this way, meaning now we are looking at this aspect. So we're looking at actually we are looking at let me make it bigger. Okay, so you have 4 here, and then you have this result on top is raised to power 4. Okay, raised to power 4. So definitely it will be the same as before.
Why is it?
Okay. Same as before.
Yeah.
Okay. Which is 256 again. So that will be the answer.
Yeah, so what I've done is
That will be the answer.
Before the meet.
So that's how these are worked out. These are how these are worked out. So you get this type of multiplication. Okay. So let's look at the next one. The rule number 3. Let me tap it from here. This is where you have this one. Okay. You have this one. So let's see how it is applied. Let's see how it is applied. Okay. Did I copy this one? Okay. Rule number 3 or property number 3. You have copy this one. Just want to illustrate how this can be done. So here we are. Go for it. Okay. Let me use this one. We are looking at this type of property. Okay. This type of property. That's the property we're looking at. So let's look at how we can apply this. Okay. This is property number 3. Okay. So property number 3. So we have bases, which is a product a times b raised power n. A times b raised power n. So it's the same as writing separate. You distribute the power. You have a to the power n times b to the power n. That's what it says. So let's say you have in here, you have, for instance, 3. Okay. Then this 3 multiplied by 2. And this product is raised to power, let's say, 2. Okay. What are we going to get? Okay, what are we going to get? So that's what we're looking at. So we are saying the same as distributing the exponent to all the bases inside here. So meaning you have in this case the 3 raised to power 2. You also have the 2, which is the base there, raised to power 2. Okay, that's what you have there. Okay, so what does it give us? What does it give us? We see that this one will be the same as 3 squared, which is 9, plus, or times rather, times 2 squared, which is 4. Okay, so if you work out that one, it will give you that is you can use a calculator. 9 times 4, it will give you 36. So that's what you get there, 36. So this is how you work out with this type of exponents. That's how the exponents can be worked out. Okay, so let's look at the third property. Third property, in this case we are looking at this one. Okay, the third property, we are looking at this one, can either be written as this first one or the next one. So let's look at this one. Okay, let's see how we can again work on it. Let's see how we can work on it. Which property is it? We are saying the fourth property. Okay, fourth property. And we want to see how we can work with the fourth property. So this is the fourth one. Okay, fourth one. Let's look at this. It's moving. Okay. Okay, fourth one. Okay, so now let's see how this can work. Looking at that, paste it there. Okay. We are looking at okay, in this particular case we are looking at this one. which is this or that. So let me expand it a bit, or make it bigger. There you are. So let me look at using the first one. Okay. This is the fourth property. It's meant to be here. Okay, fourth property. Okay. Supposed to be there. Okay, so I'm saying let's see how this is done. Okay, let me look at this one. If I use this one, okay, this is what I'm going to do. I use this one. This is what I'm going to do. Okay, first one. Let's say I have, let's say the base is the same common one. Let's say the base is 3. Even here the base is 3. Okay. Then here the power is say 4. Here the power is 2. Okay, so what will happen is it's the same as writing 3 raised to the power. So this one will be more in parentheses, but it will be the same one. Okay, so we are saying okay, so meaning you look at the first M. The power is 4. Then you have the N, which is 2. Remember? That's what we have. That's what we have. So if you work out that one, it means that you are going to have a situation where you are saying this one. Okay. This one, put it there, is simplified to be 4 minus 2 will end up to be 2. Yes, so that's what we have. That is what we have. Okay, so if you look at that, it will simply 3 squared will be 9. Do you see that? So that's the answer. Okay, or you can write it in this manner. Instead of using this, it can also be written as this to be the same thing. So let's look at this other part. If it was written as that, what are we going to come up with? Let's see. Okay, if it was like that, okay, this is what we are going to see. Okay, so when you are looking at the other presentation, so you are using the inverse of this expression. When you are looking at the inverse of the expression, then you are going to look at 1 over this come down, but the powers transpose. The powers transpose. You have N coming first, here it was coming last, and you have M coming last. In between there is a minus sign. Okay, so that's what you should remember. If you are going to express this one in form of the inverse of this, which is that, then remember that when you bring down the base below 1 here, the powers should transpose, interchange position. So that's what we have done here. So let's go for that. The base is the same, is 3. The base is the same, is 3. Raised to power, now they transpose. Okay, what was the first becomes last. It will be now 2 minus 4. Yes, 2 minus 4. So that's how it is. Okay, so now with that, then you see what happens. We have that again. So with 2 minus that means that here you are going to have the 3. Okay, the 3 is here. Okay, the 3 is here, and then this has become now minus 2. This has become now minus 2. Minus 2. Minus 2. Okay, so that's how it is. So what is the implication here? It means that you are going to have this one, okay, is the same as you can look at this in this manner to say to be the same as 1. Look at that, same as 1. Let me just put it this way again. Okay, it's the same as equals. Okay, so we are saying we have 1. Now what happens in this particular case is this is the same as looking at when it comes on up. If you have a situation you can interchange, it can come up, it changes the sign. It will now be the same as the before. What will happen is that it will now be equal to 3 raised to power 2. It will be actually this one transforms into that. Okay, it transforms into that. Okay, it transforms into that, which simply means that it will be coming out the same as the 9. Yes, that's what it is. Okay, so that's how that is done. We come to the conditionalities even here to make this one possible. There are conditionalities. What it means here is that this can be used provided m is greater than n. M is greater than n and a is not equal to 0. This conditionality is very important. This conditionality is very, very important. Why is it important? It's because if m is less than n, then it will come down as a negative like that. To come down, okay, because it will be a power raised to power n. Then power raised to power n, then it will be in the form of this one. Okay, okay. So you have 1 over the base raised by a positive number when it comes under 1. So that's why then the sense of the equation will change. The sense of the equation will change. Now again, the other point is that a should not be equal to 0. A should not be equal to 0. Okay? If a is equal to 0, the expression becomes undefined. Because even if you multiply 0 several times, how much is that 0 is 0? So that becomes undefined. Okay, so a should not be, the base should not be equal to 0 in this particular case. Okay, so if you elect to transpose the powers in this manner, then in this particular case, m should be less than n. M should be less than n. Okay, for it to hold. Okay, So that's how it is. Then A should not be equal to 0. Okay? Yeah, so that's what you should remember. Okay? So now we move on to look at the next rule. Okay. Rule number 5 in this particular case. Rule number 5 is telling us that suppose you have the expression or a mathematical statement in this manner, where you have A over B, everything raised to power n. Okay, so what it means that just like we distributed n when there was A multiplied by B, even here you must distribute n, the exponent, to the numerator as well as the denominator. So you end up having A raised to power n and then B raised to power n, provided B is not equal to 0. Okay, provided B is not equal to 0. Because if for the same reason, if B is equal to 0, then it becomes the numerator, the denominator becomes undefined. And then how many times can this 0 go into A raised to power n? It's not possible to determine. Okay, so it becomes undefined. So B should not be equal to 0. So that's how it is. Okay, so when you come to rule or quality number, property number 6, A raised to power 0, remember that any number, no matter how big the number is, provided the exponent is 0, that is always equal to 1. Okay, so that much you should know. That will always be equal to 1. Okay, then we have rule number 7 or property number 7, which says the base raised to a fraction, the base raised to a fraction, B raised to 1 over n. If B is any real number, then n is any integer, and n is greater than 1, then B to the power 1 over n is equal to the nth root of B. The nth root of B. So to demonstrate this, let me look at a question so that I illustrate this one. Okay, let's look at this one. So I'm talking about this. And maybe I use the same. No. Let me use maybe a different one. Okay, different one. There's space. Okay, let me look at this one in this manner. Okay, there we are. I'll use this one. I'm looking at this particular rule. I'm looking at this particular rule. Okay, which is this one, which is rule number 7. Rule number 7. There you are. Let me make it a bit bigger. Let me make it a bit bigger. Okay. So now, if this is the case, provided B is not equal to 0, what example can we come up with so that we show how this one is applied? So let me think about a simple one. Okay, let's say we have this situation. Okay, we have this situation. Let's say we have 9. We have 9 raised to power 1 over 2. 9 raised to power 1 over 2. Okay. Okay. Or let me put it this way. Then be 27 raised to power 1 over 3. Okay, that's fine. 27 over 1 over 3. So what is this? So let's see what happens in this particular regard. What happens in this particular regard? Okay, so what we are going to see is this transforms. Okay, this one transforms in this manner. So we come here, it will be nth root. So So we're going to take this one, and nth root will be the nth root. Okay, in this particular case, okay, it will be the nth root, okay, fine, meaning that the 27 gets inside the square root symbol, and then we find the cube root, because this is 3, we find the cube root of 27. So to find the cube root of 27, you are going to find that it will be equal to 3. Okay, is equal to 3. How? Because 3 multiplied by 3 times will be 27. 3 times 3 times 3, you're going to get 27. So the cube root will be 3. That will be the answer. Okay, are we together?
Yes.
Okay, so that's how answer this type of operations. Okay, that is using the 7th rule. Let's look at again the 8th rule. Look at the 8th rule, where you have base raised to power p over q. The indices are a fraction, whether improper fraction or proper fraction, doesn't matter. You have base raised to p over q, where b is any real number and the p and q are integers, and the q is greater than 1. Q is greater than 1. Then this particular expression, this one, which is here, is equal to, you write it in this manner. So let me again use this one and show you how this is done. Okay, we have in this particular case, okay, we have this particular case, okay, we have row number 8 rather. We have row number 8 or property 8. Property number 8, this is where we are saying it is in this manner. So what does it mean to us? Let's make it bigger. What does it mean to us? This is the same as if we have, for instance, let's say 64 is the base. Okay, 64 is the base. Think about that. 64 is the base. Find the fourth root of 64. Let me just come up with 1. Let me say 4 times 4 times 4 times, okay, so that is a cube root. Okay, cube root. Okay, let me say this is a cube root as well. So let me do this. Okay, let me do this. We have this. Okay, we have this one placed here. Now let's suppose that what we have is say 64 as a base, and then we have square 2 here over 3, 2 over 3. Okay, so that's the form it has taken. So how do we go about it? This is what we do. you are going to have this one is like saying you have this arrangement. Okay, you have this arrangement where you have this arrangement. Let me just write it properly. Okay. Okay, let me see. Okay, so you have, instead of that, you have 64 inside here, which is raised to power 1/3. Then everything, okay, is again raised to power 2. So meaning you have this type of arrangement. You have this type of arrangement. So I want to make it this manner. You have a power here. Like you have here. Let me just steal this one. Here. You have, for instance, this arrangement. I want to create a scenario like this one, where this is what we have here. Okay, yeah, okay, fine. So that's the scenario, okay? So when you look at this, what has happened is that you are simply factoring out these two. So it comes back to what did we see in this first row, this second row or first row, where row number 2 rather, you have this type of situation.
Okay.
This row number 2. So that's what we have applied actually here. Okay, so we have applied that in this manner to say, okay, you have a power raised to another power. So if you multiply the 2, you come back to the same. Are we together?
Yes, sir.
Yeah, that's what is happening. So now you sort out what is in the brackets first. So what is in the brackets first is where you apply this arrangement here. Okay, so let's go by that. Okay, so if you sort out that, what means you are saying you are now looking at a situation of this nature. You say you have, for instance, more like this one. Okay, just use that frame to create what I want. Okay, you have the cube root of what? 64.
64.
Yes, cube root of 64. So that's the inside. This is the inside. Okay, that is the inside. Now this everything has to be squared. So meaning that I can borrow, let's say, this one. Okay, I can borrow this one. Just want to create what I want again. Okay. So I put it there. Okay, but this one is what I have as inside this one. Have you seen? So that's what I want to put there. So I'll write it this way. This is what I have. Okay, that's the inside. But this power is the one which I have outside as 2. You see that? Huh? So that's what has transformed into that. Okay, so we can see that, huh? Yes, so this operation has transformed into that. So once that is done, then we can proceed to say, okay, what do we sort out inside? If you find the cube root of 64 here, you are actually going to get 4. Okay, yeah, so you are going to get 4, meaning now you can get this one. Let me just use that one to kind of reflect what we are getting into. Okay, reflect what we are getting into. Okay, then here, okay, yeah, okay, so now this one, in this particular guard, we have 4, and this power, that 2 remains, are we together?
Yes.
Okay, so we have this one. Okay, so this simplifies to that. Okay, then if you look at that, it's simply 4 square, which is going to be 16. That's the answer. You see that, huh? That's how we go about looking at that. So those are the rules which you have seen here being applied. So you should be able to manipulate these figures in this manner. Okay, you should be able to manipulate figures of exponential nature in that manner. So remember the rules, how you apply the way I've explained, that's what you'll be dealing with, okay, in these problems of this nature. Okay, so that's what you have. I didn't follow what I had prepared, but you can look at these and try them yourself using the same rules. You find that to be coming to the same kind of you try it, so you see that you can evaluate these particular problems. Okay, you can evaluate these particular problems. Okay, it should be the same. Okay, so I'm sure you can try on your own this. If you fail, then let me know. Maybe this one, the number 3 challenge, you are told that x raised power 3 over 2. I've explained how you deal with these ones. Are we together? Then you have minus 5 raised power 0. So as long as x is raised power 0, this is always equal to 1. So this will be the same as 1 times 5. Are we together?
Yes.
Okay, then this one, as I've explained, it means that you are going to find the square root of x, then raise it to power 3, as I've just explained. So once you evaluate this one, you subtract 5 times 1, which is whatever you're going to evaluate here, you subtract 1. Now in this particular case, x has been given as equal to 4. So where x is, put 4. Even here, where x is, put 4. So means that this will be 5 times 4, because x is equal to 4. But this 4 is raised to power 0. Any number raised to power 0 is 1. So that reduces to 4 to the power 0 is 1. 1 times 5 is 5. Okay? Then here it will be 4 raised to power 3 to the power raised power 3 over 2. So I've just explained what to do. Split this one. First you find the square root of 4, which is 2. Then 2 raised to power 3. So it will be 2 times 2 times 2, which is 8. So it will be 8 minus 5, which will be equal to 3 finally. Is that okay?
Yes, sir.
Okay, so that's how you look at those particular keys. So you look at these. Okay, any number raised to the power negative is expressed as an inverse 1 over that particular power. Then that power becomes positive down the 1. Is that okay? Yeah, so that's how you evaluate this particular case. The rest are just what we have been talking about. So you can try them and see what happens. Okay. Then I talked about a number of applications, okay, for indices. Where do I apply? Is it just a mere calculation and mathematics and we forget about it? No. There are a number of applications in physics, in chemistry, and in biology. Okay. In physics, we have seen exponent. Okay, the famous formula for energy, E is equal to m times c raised power 2. Okay, again here, this is how you can show the exponent with this symbol to show that this is the power. Are we together? Some calculators do show this. as a power. Is that okay? So that's what you can see there. So these are applications in physics. Okay, force is equal to ma. Okay, again, that's how it is done. Mass times acceleration, you know, that type of thing. So we also have chemistry. We have this kind of arrangement. This is a subscript, a number below. An exponent is put on top here, but when it comes below, it's known as a subscript. So it's 2 h subscript 2 or subscript 2. Okay. So again, there are a number of operations. Also in biology, we see that being shown in biology. In engineering, for instance, the electrical engineer, we have the Ohm's law, okay, which is showing that, okay, formula, okay. Then where I is the current and V is the voltage. So voltage is equal to current times resistance. R is resistance. So that is in engineering, you have these applications. We also have in structural engineer, where we start to working at the stress. Okay, how much can this particular structure withstand force, or if it is being stretched, to what extent can it resist being snapped? Okay, so that is structural engineering. So there are those. Even software engineers, you have these applications. Okay, which are seen. Okay. We also have in finance common, okay, when you're talking about compound interest, okay, you have principal times 1 plus r over n raised power nt. So that's what the formula we use. Stock and inventory growth, investment growth, you have p multiplied by 1 plus r, which is the rate of interest raised power time. Okay, all that. You are also in mortgage amortization. We have this type of application. So that's what I had for you. Unless you have any questions, we end here.
No, I don't have.
Okay, thank you so much for coming. We'll look at the next topic tomorrow. But I won't forget, I need to come up with, to make up the time, which I'm supposed to have used yesterday. I'll give you an uploaded video so that you can follow, just to cover up the time. Okay, so that you don't miss out anything. Thanks for coming. Okay, hope we'll be together tomorrow.
Yes, sir.
Okay, great.
No.